In this video, we're going to discuss how BGP actually selects the routes that it's going to use among a set of possible routes to a particular prefix. At the end of this presentation, you should be able to explain how the route selection process works. Let's start with a basic algorithm or procedure that is referred to as hot potato routing, and is analogous to the situation if you're handed a hot potato, you really want to get rid of it as fast as possible. And it is used by BGP in just one part. We're going to look at exactly how it is used in a couple of slides. But imagine that your router 1B, for example, and router 1B has two different BGP routes to prefix X. So router 1B is right there. So it's going to have one route that says that it can reach. We're going to call our interfaces here. Let's say this is interface number 1, which has an IP address. And this one right here, let's say, is interface number 2, or 3, which is also an IP address. So 1B knows that it can go to interface number 1 and go then to autonomous system number 2 and autonomous system 3 and then reach X. And it can also use interface number 3 to go directly to autonomous system number 3 and reach X. So those are the two routes that it knows that it can reach. And it's going to actually select the route with the least cost path to the next hop router. And what this means is that imagine that the least cost paths are selected based on the number of hops. So if your router 1B, in order to reach interface number 1, you will have to go through this link between 1B and 1C, and then the link between 1C and 2A. So if we're talking about reaching interface number 1, it has a cost of 2 hops. But if we're talking about reaching interface number 3, it has a cost of 1, 2, and 3 hops, assuming that the least cost path is computed as the number of hops between routers. So what's going to happen is that router 1B is going to select interface number 1 to reach the prefix X. So router 1B, let me put it here, is going to add to its routing table an entry that looks like this. It's going to say that in order to reach prefix X, it has to use interface number 1. Even though there's the fastest path that goes through a fewer number of routers, notice that that is the case, we will go directly to AS3. But in hot potato routing, that doesn't matter, and the entry that is added to the table, the routing table for 1B, is that one. Now, the route selection process in BGP is a little bit more elaborated than that. Hot potato routing is just one part of the solution, and what we're going to use is an additional BGP attribute. Remember that before we talk about two BGP attributes, the next hop and the AS path, we're going to add another one called the local preference value, which is another BGP attribute, which is set basically by the administrator of the autonomous system. And this actually could be also set by the router, or from your autonomous system, or from another router in the same autonomous system. But every BGP route, along with its two attributes, AS path and next hop, is going to have also a local preference value. So how does the actual route selection algorithm works? So remember that our router 1B here has actually multiple routes to its destination, prefix X. So what's going to happen is that if there's more than one route, BGP is going to use 4 elimination rules in the following order. First, it's going to pick the route that has the highest local preference value. And if 2 or more routes have the local preference value, what it's going to do is going to select the one with the shortest AS path. So this is the same as using distance vector, or similar to using distance vector, with the number of autonomous systems as the metric. And if after that you still have more than one route left from the remaining ones that have the same local preference value and the same AS path length, then it's going to use hot potato routing. So basically that's the route with the closest next hop. If after that it still has two or more routes have the same local preference value, the same AS path length, and the same closest next hop cost, then from the remaining routes it's going to use the standard identifier, something called a BGP identifier, and depending on the identifier and the way that the identifier is created, BGP selects one of the remaining routes. Okay, we're not going to look at the details for the BGP identifiers, and that's how the route selection algorithm works. Now let's look at a more realistic view of the internet. And the internet, actually, you have different sizes of autonomous systems. You have tier 1 autonomous systems, like the ones owned by very large network, like AT&T's backbone network, or maybe Deutsche Telekom in Europe, or NTT in Japan, or also worldwide networks like what used to be Level 3's network. Now it's owned by another company called CenturyLink, for the time being, at least. So these are tier 1. These are tier 1 autonomous systems. There's also smaller autonomous systems, like this one, which will be an ISP, a typical ISP or a large corporation. There are smaller ones. And notice that depending on how you're connected to the internet, you have different capabilities. So for instance, AS6 here is a stub autonomous system because it only has connectivity to one autonomous system, which is AS1. The same as AS5 is also a stub autonomous system. However, AS4 is a multi-home autonomous system because it has connection to two other autonomous systems, in this case AS2 and AS3. And the policies change based on who you are. So for instance, a tier 1 autonomous system might be in charge of routing traffic, or might have traffic agreements of routing traffic, let's say from AS3 through AS2 to AS1 to AS6. So AS2 might have an agreement to do that, or might actually not have that agreement. And if there's traffic from AS3 that needs to go to AS6, maybe AS2 is not going to cooperate and use and advertise a route to AS6 through AS1 to AS3. So AS2 might choose not to tell AS3 that it can do this, that it can reach AS6. Or it might actually, if there's agreement between service providers, that might be the case. But those agreements are confidential, and it's hard to keep track of how these agreements change over time. On the other hand, a multi-home autonomous system like AS4, let's say there is a company that has connected to two different service providers, one being the backup of the other, then it's definitely not in the business of forwarding traffic between AS2 and AS3. So let's say that there's traffic that needs to go towards AS5. So AS4 is likely not going to advertise any route towards AS5 to AS2, or so that it does not participate in the process of forwarding traffic between two different autonomous systems. It will only be interested in forwarding traffic to them, but not between them.